our company, INOVA Geophysical, we are land seismic equipment manufacturers. So I wanted to give you a bit of perspective of some of the trends, the technology trends and challenges that we see in our business. So the agenda today, I'm going to just quickly talk a little bit about the current state of the onshore market, which is, you probably all realize, is quite tough at the moment. And then I'll look at a few areas that we're certainly heavily involved in, which is integrated broadband acquisition. I want to look also at some of the challenges as we really increase our channel counts. What does that really mean for data rates and data storage? Because there's some scary numbers there when you start looking at it. And then environmental footprint is another challenging area as oil companies go into more and more difficult areas, environmentally sensitive areas. What can we do to help in that situation? And then, there's been a lot of talk about remotely piloted aircrafts and so on. So I've got an example of some work that we're doing in that field as well. So just a little bit about the market. I'm sure everyone here is aware that certainly our business, our market is under a lot of pressure at the moment. The oil companies are finding that their costs are increasing. Their focus is turning more towards production. The oil and gas price is declining. There's all sorts of geopolitical uncertainties everywhere. So it's very tough, and it's all meaning that exploration activity is quite substantially reduced at the moment. And of course, we're starting to see some consolidation in our industry as well, with companies coming together. But there are some bright spots, I would say. The Middle East is still a healthy area, certainly for us at the moment. There's a lot of investment still going on, a lot of surveys planned in the future in there. So that's a good sort of bright spot at the moment. And I think also, there is just a continual push for improvement in technology and, of course, lower costs. But I want to just, provide you with, I think, a different angle on the size of the market and the spending that's going on in the market compared to one of our previous presenters. I mean, what I'm trying to show here is this is over about 15 years. The equipment spend, this is the total sum of money being spent on onshore seismic equipment. That's the blue graphs there. And I think what you can see is it's generally been pretty flat. The spending is flat. The spending is not substantially increasing. We had a slight uplift sort of mid-2000s when the first of the super crews began to emerge. But this creates this kind of flat spending with the need for technology improvement. It does create difficulties for companies like ourselves and also for contractors, because we're helping the market acquire much more data, better productivity, better quality, but the volume of spend is not increasing. So there's an issue, there's a challenge there. How do we fund that development? It's a difficult problem. And hopefully we may see in the next 10 years another step up in spending. That would certainly help a lot of us in the market at the moment. So just going on now to talk about technology. And the first thing I want to talk about is Vibrasize, which is still by far the most common source used in onshore exploration. So broadband is something where we're seeing the demand for broadband acquisition really growing rapidly. Lots of places, lots of oil companies now are really starting to look seriously at it. There's a lot of reasons why. Obviously, deeper targets, better resolution, some complex geology that people want to image, what it's doing to help full waveform inversion and velocity models and so on. So there is a real increase in interest there, and I think to be fair, I think we're still learning a lot about the benefits of these real low frequencies. I think we're still quite early in that cycle in terms of understanding what they can do for us. But my point here is that there are broadband solutions here now. They are available. We have been involved in several projects in various locations where we see starting frequencies as low as 1.5 hertz. We think we can go down even further, and I'll show you some examples of that. Also at the high end, we're seeing 150, 250 hertz being sought after and actually being delivered by some of the equipment that we are producing. And also, as well as the source, we've got to consider the sensors and the systems. And MEMS sensor technology continues to develop, and I'll show you some examples of how MEMS is an ideal sensor for capturing this low frequency data. And of course, acquisition systems are essential in terms of really being able to capture this acquisition in a very productive way with many channels. So this is an example that we've been given permission to show from PDO in Oman. And what we're looking at here actually is a continuous section where the first part, the left-hand side of this section, was actually shot with a more conventional sweep. This is 6 to 86 hertz, but halfway through this project, they decided to extend the bandwidth and went down to 1.5 hertz. And interestingly enough, again, one of the previous speakers showed a picture of a Vibrasize sunk in the Sabka. This particular project used both heavy vibes, 80,000 pound vibes, and small mini vibes. And the mini vibes were actually used to drive across the Sabka without sinking, and the client in this case achieved fantastic coverage of his area with the mini vibes skimming over the top of the Sabka. They didn't sink, and they also generated this broadband data. So this is the same data set, just with a bandpass filter between 1.5 and 6 hertz. And I just wanted to show you this just to show that this energy is present and it exists. This low frequency energy is capable of being generated in terrains like Oman. So that's a little bit on the. Hold on a second. There's something here. There's some slides missing here. Okay, I don't know what's happened to those slides, but. Switch now to high frequency. Sorry, this is the wrong slide deck. Sorry, there's a problem here. Can you make sure this is the final version? This one here. This is an abbreviated deck. Sorry, this is not the deck we practiced earlier on.
BC isn't on Chinese time, is it?
No.
No, seriously, I've seen this happen before.
No. No, there's.
Because the server that it gets put on has got a different time zone, and it thinks too smart, so it puts the previous.
No, I think we've got the wrong version on there. Let me see. Yep. Wrong version. Okay. I'll just continue. It's okay.
I was once in China, just to make some fun out of this, when a porn video came up. And it wasn't on my screen, it was on the screen up on the front. Everybody's laughing at me.
Okay, I'll just continue. What I was going to show, actually, I'll just describe it. Actually, is some tests that we have been doing with a prototype Vibrasize, looking again at improving the low frequency output of these vibes. So we have done some tests recently where we had a downhole sensor down about 7,500 feet, and we were recording 0.5 hertz data, and we've seen some very strong output at 0.5 hertz with some prototype Vibrasize development. And the energy that we're able to generate is almost double, if not even more than double, what our current state-of-the-art heavy Vibrasize is capable of. And also what it means is not only are you getting much more signal into the ground, but you're also able to get to those low frequencies quicker. So it means that your productivity is substantially improved. So we've also been doing work on the high frequency side. What we're seeing on the high end is a lot of growth in these mini vibes. The mini vibes are being sought after a lot, again, for their environmental impact. They're very small and very maneuverable, but they have now got this very high performance, right up to 400 hertz. We've been able to shake those vibes, and again, we've done some tests where we looked at some downhole data, and we are seeing very clear, coherent energy down at, again, 7,500 feet. We're seeing 150, 140 hertz, and 7,500 feet is about halfway through the Boland Shale here in the UK. So these little machines, they're capable of really nice maneuvering, low impact, and generating tremendous broadband energy from these systems. So that's Vibrasize. I wanted to talk a little bit now about sensors. So this is actually the results of, this is something that happened while we were doing some tests in Canada. We were doing, as it happened, some low frequency testing in Alberta, and as we were doing these tests, there happened to be a magnitude 6.3 earthquake just off the Vancouver Island. So there were a number of different sensors involved in this test. This here happened to be a seismometer. So what we're looking at here is 30 seconds of recording. VP218 is the shot just before the earthquake. 209 is the shot on the earthquake, and 208 is some ringing after the earthquake. I'll have you.
If you want to go back to that, then you're welcome to.
Yeah, please do.
Yeah. Okay.
Right. Go for it.
So you should be able to find the right slide.
Okay. Now, or has it been changed?
Yes, it should be changed. Yeah.
Okay, let me try it. I'll go back to it. Hello? Okay, I can wait. I can wait. Yeah. Well, I think has someone been to the bar first or something? I don't know. Okay. Okay. No, still the same version. Never mind. So this was the data as it was recorded by a seismometer. So you can see very clearly here the low frequency energy coming through very strongly in the seismometer, and the ringing on the subsequent shot as well. And this is the same data as it was recorded by a 10 hertz geophone, a standard geophone. So you can just about make out the earthquake event there in the middle panel, and again even fainter on the right-hand panel as well. But this was how it was recorded with a MEMS sensor. This is actually a Vibrasize sensor that was used in this test. So again, you can see the low frequency energy, 0.4 hertz, recorded very strongly in this with this MEMS sensor, and even the right-hand panel showing the ringing coming through here. So the point, really that we're making here is that this is an excellent sensor for recording these low-frequency events, which the Vibrasize technology is now capable of producing. So this sensor technology is continuing to develop. We now have really done a lot of work in terms of engineering these sensor packages so that they are very small, they're very low power, and they're very highly and tightly integrated with acquisition systems. This is our 1C MEMS sensor in a very small package. You can see some of the parameters of that. They're only 85 milliwatts and 175 grams. And in fact, when you combine this in a high density integration with our cable system, you actually have a power consumption per channel which is less than an equivalent analog system, which I think is the first time the industry's really seen that kind of progress. So MEMS sensors in a small form are now very economical and very operationally effective as well. Okay, so moving on now to acquisition systems. So we do continue to sell a lot of cable systems. I know people were talking about the cableless market earlier on, and I think we still see that the cable market is strong. It's about 80–85% of the total number of channels out there. The costs are reducing very substantially. A cable system still costs substantially less per channel than a cableless system. So there's still a big market out there, and we are continuing to onward develop our cable systems. And from our perspective, there are I suppose 3 key things that a cable system, acquisition system, has to do. It has to be scalable from 2D right up through the high channel counts into more complex, high productivity Vibrasize. It has to be well integrated, not only with the single sensor technology that I just described, but also for transition zone or for hybrid operations with cableless systems, with cableless nodes. And also productivity is a really critical factor now. A lot of these systems are deployed in 50, 60, 100,000 channel configurations in the Middle East with incredible productivity now. I mean, the productivity that we get in the Middle East is phenomenal, purely because of things like simultaneous sweeps, things like distance separated acquisition. So that's a huge focus area for us as well, is to keep that productivity very high. Okay, another couple of slides missing, but never mind. So what I wanted to point out here, though, is with this growing drive for more and more channels, I think it's time that we kind of took stock a little bit and said, well, hold on a minute. We actually thought about the consequences of this, and is IT really up to the job here? I've picked out a couple of examples. I'll explain this graph now, actually. So what we're looking at in the bottom axis is channel count, going up to the famous 1 million channels, which people are talking about, and then also the data rate is on the vertical scale here. The blue and the red and the green is a sample interval, so we're focusing on a 2 mil sample rate here. So if I pick out 250,000 channels, what does that mean in terms of raw seismic data coming up the cable? So our calculations of that is about 4 to 5 gigabits per second. If we go up to 500 channels, then we're up to 8 or 9 gigabits per second. So that's a tremendous amount of data coming up the cable towards a system which has got to handle this, process it, record it, and so on. So if we look at some of the devices out there, someone earlier talked about tape drives, and a tape drive nowadays is maybe capable of between 160 and 250 megabytes per second. So clearly that's not going to cut it in real time. The sort of state-of-the-art disks, the solid-state disks, flash drives, you maybe get between 500 and 600 megabytes per second. If you stick these into a RAID array, maybe like 16 1 terabyte arrays, that's quite quite a chunk of hardware. You may get the RAID performance up to possibly 3 or 4 gigabytes per second. So we're getting into the ballpark there. But once you integrate a disk drive into a system, once you think about the processor usage, the data bus contention, the I/O bottlenecks, memory, cache, drivers, applications, correlation, QC, you suddenly see that actual throughput onto your recording device really comes down. So I think the point is that we're right on the edge of what's capable and also what's supportable in the field. And you've got to remember that. We've got to have field engineers that are capable of installing and supporting this kind of technology. So it's a very big challenge, taking an acquisition system up from 250,000 channel, which some systems can do right now, up to 500 and even beyond that. So a little bit of caution there, just for everyone. And then if you think about data storage as well, the same graph basically, but now I'm looking at how much data is actually stored on a 24-hour basis. So if you look at a 250,000 channel system, you're talking about 43 terabytes of raw data per day at 250,000 channels at 2 mils. It's a huge amount of data. 500,000 channels, you're up to 86 terabytes of raw data on a 24-hour basis. So if you think about a 500,000 channel project over a 6-month period, you're talking about potentially something like 12 petabytes of data storage. And a petabyte these days, going rate for a petabyte is about $200,000. So you could be talking about over $2 million just for your data storage. It's a massive cost, and as we demand more and more channels, I think we're going to be really challenged to actually solve this sort of problem. So I think maybe we'll see a little bit of a plateau in what people need in terms of channel counts till they understand better how to handle this kind of volume of data and get to grips with the cost of it as well. Okay, I want to switch now to thinking about environmental impact. As I said earlier, there's a lot of oil companies are moving into sensitive areas, maybe into urban areas. You think of the shale gas opportunity maybe in the UK or otherwise, other places in Europe, and this is becoming a very important issue. So how can we reduce the impact in these areas? And the challenges for operators going in there are do I really need to do as much line cutting as previously I've had to do? Do I really need to use as much dynamite as I'm expecting to? What am I going to do about the environment and the wildlife? And what about the urban visibility or the so-called social cost of shooting seismic? You go into a village in Bangladesh or drive through the streets of North Yorkshire or something. What am I going to do to try and kind of mitigate those, and what can what can seismic equipment providers do to help that? The picture I'm showing there is courtesy of Total, and they recently completed a survey in the Ugandan national parks, and they spent I think something like 2.5 years prior to starting that job negotiating permits, negotiating how they were going to acquire this project in Uganda. As it happens, they executed that project very, very successfully with the use of cableless technology and these small vibes, which I'm going to talk about. So small vibes we see as definitely an emerging technology, an emerging product in the market. They've obviously got lower weight, so the access to whether it's thawing ice or crossing bridges or small roads or oil field infrastructure is a clear benefit. They're now road legal for use in the EU. They've got small length and width, so the line cutting is reduced. They can be fitted with tracks, so they can move, up slopes or difficult terrain. And they've got this real broadband energy capability now. So again, these machines now can output super signals from about 1 to 400 hertz, and at significant depth as well. This is an example from the US, the South Georgia Rift Basin. This is some data that was acquired with two of these small vibes, two of the UNIVibes, with a 6 to 76 hertz sweep at 70% force. And the key takeaway here is that those small vibes have been able to bring out a structure at 10,000 feet with those two vibes. And obviously it's conditions dependent and whatever, but I think this is a good example of the kind of force energy penetration that these small vibes can achieve. And 10,000 feet, by the way, is the very bottom of the Bowland Shale here in the UK. So small vibes, we think, definitely have a place in terms of reducing this environmental footprint. And the other technology that's key here is cableless, for sure. I think we've been talking a little bit about cableless already. I think we're all realised that the impact of cableless is growing as people are realising the benefits of this environmental impact, reducing their HSE exposure, smaller crews, unconstrained deployment, and so on. And we're certainly seeing the geographical spread of cableless systems growing. It's still very dominated by North America, but we're seeing systems now deployed in Africa and Asia and Europe and South America as well. And I think the market, in terms of the type of cableless system, certainly we see it being split really between what we would call blind nodes and nodes which provide some form of status. And I would differentiate them between what I would call real-time nodes, which transmit the data in real time, because that's still a very small part of the overall market. So again, some kind of new features or new ideas with cableless. I think most modern cableless systems can certainly handle multiple sensor types, whether they're geophones or these MEMS sensors that I previously described. So if you think about a cableless system, small compact cableless system with a string of 3 single sensor MEMS in a high density configuration, there you've got a very light package, able to acquire very good broadband data in a high density configuration and very easy to carry and portable and so on. Also, power consumption is, that is just improving all the time. We're now capable of easily 20 to 30 days power consumption in the field, which means that people don't have to go in and out of the field to pick up the batteries, change the batteries and so on. So again, reducing the impact. And also it's possible to do some very simple status QC or even noise monitoring without the need for any complex radio infrastructure. And it's very simple to do that with a Wi-Fi connection, with a small tablet computer. You can walk out there in the field, you can go in an ATV, or you can go in a helicopter. So there's various ways of achieving that and getting some confidence in the spread without necessarily having complex radio systems out there. And one of the things that we've been looking at in this regard is could we supplement that capability with a UAV? So we're working with a contractor partner to basically take a UAV. We're just at the experimental stage at the moment, but we take a UAV and we basically add a very small compact computer to that, load it up with our QC software. We stick a Wi-Fi antenna on there, and we can put a QC package together on a UAV. The type of UAV we're looking at is a fixed-wing machine. The flight time is typically 2 hours, and it has a 5-pound payload. So these units, these UAVs, are cost about $150,000. So not hugely expensive, but they offer really significant efficiencies in the contractor's domain, certainly. Let me just go back. One of the things that we've found is that if you take a typical QC operation, a cableless QC operation today, using an ATV. Over a 2-hour period, these guys might achieve maybe 1 or 2 lines. They may be able to QC 1 or 2 lines. With the UAV, you're looking at more like 9 or 10 lines in that 2-hour period. So there's a 4 or 5x at least productivity improvement. And also, a lot of the guys in North America currently use helicopters for this operation. A helicopter typically costs between $10,000 and $15,000 per day out there. So again, you're saving that cost and that time. So we think there's this is definitely got some room to grow. The licensing issue, the regulation issue, is certainly something that needs to be further understood. But we see definitely some potential there for nice, efficient operations. Okay, so just to conclude then, apologies for the shortened version here, but there were some extra displays I wanted to show you. But I wanted to just conclude here by saying that certainly our view of the direction of onshore technology, onshore exploration technology is certainly broadband. There's a huge focus on broadband, and our position is that with broadband you've got to think about a balance of technology. You've got to think about the sources, yes, but also what sensors are you using, what systems are you using. Do you have the integrated technology that you need to really acquire broadband? And at the same time, productivity is a huge focus, and will continue to be that, and we'll see some more use of automation, UAVs and so on. And the other flip side of that is how do we get in and operate with a minimal environmental footprint, and not reduce the social cost that we're talking about. So that's our view of where we see the onshore technology go. Okay, so thanks very much for your time. Apologies for the short time.
No problem. So, any questions? Well, let me ask one before that boring person in the middle talks.
Yeah.
So you said halfway through you had a slide which had a sort of right-hand end of the axis, 1 million channels.
Yeah.
And you said people are talking about that. I mean, actually, probably Shell have been talking about that for 5 years, or I don't know, maybe more.
Yeah.
You think that's what it is, just talking?
Well, I think we've got to get there. We may get there eventually, but I think we'll take small steps to get there. You saw the cost of just storage, and then the logistics of actually putting that into the field. It's a huge challenge. So maybe we need to see some kind of advances in storage technology that will get that cost down, that size down, that complexity down before we really hit 1 million channels. I think it's a great aspiration, and we will probably get there. But I think we've got to take small steps along the way.
Okay. So, Chris, go ahead.
Great talk, Andy. Really interesting. Sorry we missed the other side. We can but guess. You showed a really impressive low-end response for that MEMS device. How have you overcome the 1/f noise that has traditionally plagued MEMS sensors? And if that's correct, will you sell it to us?
Yeah, I think 1/f noise is it's an intrinsic part of these MEMS sensors. It typically, certainly in our system, it starts to kick in about 3 Hertz, and we see that. So there's certainly advances that we think are possible in that side of things.
You showed 0.4 Hertz.
I showed 0.4 Hertz, absolutely.
So quite clearly you're able to, I mean, okay, it's an earthquake, so you've got huge signal.
Huge signal, yeah, absolutely.
But nonetheless, historically you would have had a blocking filter.
Yeah, so
Because the 1/f noise was so bad.
yeah, well, we take those low cut filters out, no problem. Noise floor will come down. There's no question that noise floor will come down. There's a roadmap there. I think, you know, we can come at it in two ways, though, Chris, because we have the source technology. We're coming at it also from source. We're trying to really boost that signal as well. So we're going to almost double that. You know, that signal strength coming out of these low frequency vibes, which will help also.
Stuff to do in the ring.
Yep.
Great talk and great technology.
Mine's more of a comment because, well, Andy works with me, so, but it's response to your comment. Oman, PDO, which is part of, 35% owned by Shell, is talking about 500,000 channel tenders within the next year. So it's coming. It's whether it's possible or not. Even that's, for example, $100 a channel with 500,000 channels. You're now beyond the capital budget of almost every single seismic contractor that there is. So there is that capital constraint challenge as well, which means 7-8 year contracts from the oil companies. A lot of them are not prepared to do that.
Interesting. Okay. Ian, please. Oh, but no, stop there.
Looking at the technology here, the bar Oman, a lot of this seems to be focused towards the continental US. When you're going into Africa, where you potentially have got countries that require a much higher local content, are you having problems with the technology not meshing with your user base? Or are you having to put more expats in to manage potentially losing the value of very cost-efficient local content?
Well, I think that's really a question for the contractors to answer. I mean, you know, we supply the equipment to the contractors, and it's up to them to staff the crews accordingly. I'm not aware of any problems in terms of local content, but I would say that the contractors also are finding, you know, this kind of relentless drive for more channels and higher productivity is actually a challenge for them as well, because, you know, they have a lot more schedule risk. Their jobs finish quicker. They don't have the backlog that they need to really move into countries like the Middle East. So they're challenged by this as well.
Okay, Ian.
Yeah, thanks, Andy. I think you showed a picture of the one component sensor.
Yeah.
On land, do you see 3 components as kind of disappearing or increasing, or what?
Well, it's interesting. I think you know, you'll know this as well as anyone. I think the challenge with 3 component has always been on the processing side, and that's really sort of prevented its uptake. But I think you know, I do see people looking at it again with broadband in mind and with full waveform reversion in mind. So we're certainly you know, it's continuing as a product line in our company. It's whether it has a renaissance, I don't know, but we're more focused on, you know, the MEMS as a good broadband sensor, and to get it into a more cost-effective, high-density configuration. That's really where our focus is.
Thanks. Yeah, maybe a second comment really. I don't think you should think of 1 million as your aspiration. I think you should up that to, you know, 5 million or 10 million. And I say that advisedly because if you follow the material that comes out of, say, Kansas University, who specialise in near-surface work, the complexity of the near-surface inland is so difficult that you need these channels.
Yeah, but again, Ian, I think the problem with that is the business model is broken. For a contractor to take that kind of capex responsibility, the business model doesn't work. So that there needs to be some new thinking there in terms of how is that funded, how is that paid for, because it just cannot happen right now. That's the problem, really. Yeah.
Okay, good. Anybody else? Well, thanks, Andy.
Okay.
Thank you very much.
Thanks.
Great talk.